Greetings to all you exquisitely inquisitive ladies, gentlemen, and scholars, and welcome to Natural Philosophy with J. Allen. In this episode, we shall be looking at the Lorentz Contraction formula as it pertains to the special theory of relativity. And so we shall be taking the limit of the Lorentz Contraction formula in order to see how the speed of light affects the length of an object. So let's get at it, shall we? However, before we get into the Lorentz Contraction formula, I would like to present to you some of the principles of limits, because we haven't really gotten into that idea, and it's pretty important, I'd say, in order to understand the Lorentz Contraction formula. So mind you, this is only a few of the limits, about half actually, of the limit principles, I should say. So number one is the limit as x approaches a of f of x plus or minus g of x equals the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. So what this is saying basically is that you can separate the functions, or you could think of it as terms. You can separate the terms and take the limit of each term individually. So let's say that this is x squared and this is 4, so you just say the limit as x approaches a of x squared plus or minus the limit as x approaches a of 4 or 3 or 100 or pi or whatever you have. So it's pretty simple, and all the other ones work like that, where you're just basically separating each individual term of function and taking the limit of each individually. And now here I have number 2, where we have the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f of x over the limit as x approaches a of g of x. So again, you can see that all we're really doing is, when we're taking the limit of a function, is we're separating the two functions and taking the limit of both the functions or terms. Like I said, you can think of it as just a term here. Like, say this is x squared, and this is just a constant, like the number 4. You could say that you're taking the limit as x approaches a of x squared over the limit as x approaches a of 4. So for principle number 3, we have the limit as x approaches a of the root of f of x. So the root could be, you could have a 2 in here, or a 3 or a 4, but whatever root you have, that root of the f of x will equal the root of the entire limit as x approaches a of f of x. So what you do is you just pull the root outside of the entire problem, and you stuff the limit as x approaches a of f of x inside the root. As you can see, all these principles are pretty intuitive, and the last two are actually the easiest of all. All you have to do here is, when you're taking the limit of a constant, any constant, such as if the constant is a value 4, or if the constant is 100, whatever the constant is, if you take the limit as x approaches a of that constant, the limit will equal the constant. So the limit of a constant equals the constant. And for number 5, the limit as x approaches a of a variable, any variable, will equal what the variable is approaching. So the limit as x approaches a of x equals a. What the variable was approaching, that's what it equals. So that's all the principles. Now we'll go on to the problem. As you can see, my board needs to expand in size a bit, but we're going to try it this way. In the theory of relativity, the Lorentz contraction formula L equals L sub 0 Actually, this could be a L or an L. Either way would work when it comes to this this formula here. So L equals L sub 0, the radical of 1 minus v squared over c squared, and this is velocity squared over the speed of light squared, expresses the length L of an object as a function of its velocity v with respect to an observer, where L sub 0 is the length of the object at rest and c is the speed of light. Find the limit of L as x approaches c from the left side of the number line. That c minus there, it means that you're not coming from the right side of the number line, the positive side of the number line. You're coming from the negative end of the number line, and we'll get into why that's true in a minute. Right, so that might seem pretty daunting to anyone who's just starting out in calculus. Basically, all we're trying to do is to take the limit of this function. But it's interesting to note that what we're looking at here is what happens to an object when it's approaching the speed of light. And from the perspective of the object, nothing's really strange. But to an observer, this would represent what an observer sees when an object isn't moving. But all of this represents what an observer is seeing in relation to moving towards the speed of light. And we don't really need to know how this works for the time being. So what we're going to do is take the limit as x approaches c from the left side, and all of this would equal the limit as x approaches c from the left side of L sub 0 radical 1 minus v squared over c squared. So we're going to use the limit principles to break all of this apart. Right, so this is what everything would look like when you separate everything out. And I did skip a step, but I'll explain what I did. So the first principle is you take the function, when you're adding two functions together, you take the limit of the one function and then you take the limit of the other function that you're adding together. In this case, we're subtracting. Oh, and I apologize, but I had x here for the variable when it's really it should be v, because the variable is velocity. But anyway, when you're taking two functions, you separate them. And that's what we did here. So we took the limit of 1 as x approaches c from the left side minus the limit of the fraction. And what I did here, I took the limit of the fraction, but because it's a fraction, well, you have to take the limit of the numerator and you have to take the limit of the denominator. Right, so it's pretty simple to understand that you're not going to just take the limit of the fraction as a whole. You're going to take the limit of the numerator and the denominator. So now the third principle was that you pull the radical out onto the outside and you have all your limits on the inside of the radical. And for the fourth and the fifth principle, what we need to do is actually take the limits of these things. So the limit of 1 as x approaches c from the left side would equal 1, because the limit of a constant is always a constant, and 1 is a constant. It's always a 1, it never changes, so it's constantly 1. So 1. Then we have minus, and now the limit of v squared, velocity squared, as v approaches c from the left side would equal c, because that's the fifth principle, where you have the limit of a variable. As the variable is approaching a number, that variable equals that number. That should make sense. When a variable is approaching a number, that variable is getting closer and closer and closer to that number. And it's when you're taking limits, the variable is getting ridiculously close to the number, but it never actually becomes that number. So the limit of v squared as v approaches c from the left side is going to be c squared. Because you just simply plug the c into the v. Only that's not entirely what's going on. You're not plugging in c, you're plugging in an approximation of c. And the limit of c squared as v approaches c would be c squared, because the limit of a constant is always a constant, and c will always be c. C is an actual number that doesn't change. It's not a variable, it's a constant. So this would be c squared. Just one down, and extend that. And so we have the radical of 1 minus c squared over c squared. And obviously when you have a number over the same number, all that will equal is 1, right? So we have 1 minus 1. And obviously that will equal radical 0, which equals 0. And so what does that mean for us? What we were doing was we were looking for what the length would be when the velocity is approaching the speed of light. So the length, it's interesting, the length of an object from an observer's perspective who's outside and watching the object or spacecraft from afar would see the velocity of the object as it's approaching the speed of light would be contracting. That's why it's called the Lorentz Contraction formula, because the object would be contracting the faster it goes. And that's true for anything. The faster you move through space, your length is actually shrinking. But when obviously you don't perceive that, but when you're approaching the speed of light, it would be very obvious to the observer that you're contracting, you're shrinking down in size. So most people are aware that time is relative, but what might not be so obvious is that length is also relative when you're going different speeds. So it all has to do with how space and time intertwined. They're two sides of the same coin. So the faster you're moving through space, your personal dimensions are being affected. So that represents as you're approaching the speed of light, you're shrinking down to 0 size. And interesting enough, even though you're shrinking down to 0 size, your mass, your density, is approaching infinity. Pretty hard to wrap your mind around, but it's how special relativity works. So the easiest way to travel through space, I find, is to warp space and time, of course, because when you're warping space, you're also warping time. So when I'm traveling through space, I prefer to warp space by contracting the space in front of me and expanding the space behind me, and that creates a wave, and I just travel the wave. My spaceship creates the energy that allows space to move faster than the speed of light. So my ship, it's just at rest, it's right here. So that's the easiest way I find to travel through space, is to just warp space and travel the waves of space as it's moving faster than the speed of light. I don't know of any technology yet. I know of many space traveling technologies, but I don't know of any space technology that even gets to half of the speed of light before radiation starts to affect you in horrible ways. And even when you're traveling at half the speed of light, it's most uncomfortable. So I don't recommend it. I recommend that you simply warp space and time. Your ship is simply riding the waves of space-time as your ship isn't even moving. It's just in this happy little bubble. That's how I enjoy traveling. I don't know. How would you enjoy it? Maybe you've experienced space travel yourself. I don't know you, so maybe you could leave a comment below and you could tell me how your favorite way of traveling through space functions. And that's about all I have for you today. So I personally, I had fun. I find this subject absolutely exquisitely fascinating and fantastic in every way. So I had fun. I hope that you had fun. And if you did, like and subscribe. That would be so lovely. Thank you. And have a good day.